Hello and welcome to the Class 11 video. Today we will be discussing reasoning with generalizations. People make generalizations all the time. I just made one right now. But of course, making generalizations can get you in trouble. People don't like it when you apply generalizations to them. In fact, sometimes it's suggested that the way to avoid racism is never to make generalizations at all. But even when I was just making that statement, people don't like it when you apply generalizations to them. I was making a generalization. So we can't think at all without generalizations. And so the topic of this video is a little bit about how to do it well, how to make generalizations well. In this video, we're going to be looking at two argument schemes. One where we start with experience in the world and draw a generalization from it, and one where we start with a generalization and look at how we apply it to a particular individual or situation we encounter. As we did with arguments by analogy and arguments from authority, each of these arguments will have a special way you have to put the argument in standard form and special critical questions you should ask to be sure you are avoiding fallacies. The first argument scheme we are going to look at is inductive generalization. Inductive generalization is just reasoning from particulars to a generalization. So you start with statements about particular objects and you wind up with a generalization. Standard example here is the generalization that all swans are white. Europeans, for the longest time, had this idea, a biological generalization, that all swans were white. Then they traveled to Australia and discovered a black swan. So the generalization turned out to be false. Ever since then, this has been used as a standard example both of inductive generalization and how it can go wrong. So this slide is just an intuitive representation of what's going on with inductive generalization. On the lower part of the slide, you see images of clip art swans that represent particular experiences you might have. Look over here, this is a white swan. Look over here, this is a white swan. Here's a white swan, here's a white swan, here's a white swan. All of these swans surround the word particulars. Then there's an arrow going up to the general statement that all swans are white. So the general statement was inferred after having repeated experiences with individual swans and discovering they all were white. We can imagine putting this inference in standard form like this. P1, I have seen 100 swans. P2, every one of those swans was white. Conclusion, all swans are white. The instantiation syllogism is the form of reasoning that goes in the other direction. You start with a quantified categorical statement in the premises. I'll explain what that term means in a second. Really, you just start with a generalization in the premises. And then you go to a particular, right? So you might start with all swans are white, and then you go down to a particular statement, Odette the swan is probably white. Odette was the name of the swan in the ballet Swan Lake. So on this slide, the heading is generalization, and that generalization is just that all swans are white. Then there's a big arrow pointing down to the word particulars, and there's another clip art swan who's labeled Odette, and the statement is Odette the swan is probably white. And we can represent this inference like this. All swans are white, Odette is a swan, Odette is white. Interestingly, this one argument is different than almost every other argument we've looked at so far when we started talking about particular forms of arguments and argumentation schemes. Generally, when all the arguments we've been talking about up to this point have been inductive. Remember, induction is the kind of argument where you are only aiming at strength. You aren't trying to be deductively valid. So the premises, if they were true, would only make the conclusion likely. The conclusion wouldn't have to be true if the premises were true. All of the arguments we've been dealing with up to this point have been inductive. If you infer something by analogy or on the basis of someone else's say-so, you could be wrong. And this is because the conclusion has content that goes beyond what is said in the premises. And in deductive reasoning, you're just sort of restating or rearranging the information that's in the premises. With inductive generalization, the arrow going up, we were also being inductive, just like the name says. But now here, in instantiation syllogism, there is one case where we are actually being deductive. And that is if the generalization we use has that word all in it. If the generalization has that word all in it, then we've basically taken on all the risk that normally comes with induction and put it in the truth of that premise. So now, instead of making a risky inference, you have a premise that's likely to be false because it makes it makes a really big claim. So in this case, actually, this is an example of a valid argument, but not sound, because it turns out that not all swans are white. All right, so let's look at a couple of other examples. P1, we surveyed 3,000 likely voters. P2, 57%, said that they would vote for Biden over Trump. Conclusion, Trump will lose the election. So now, take a second. Is this inductive generalization, going from particulars to a bigger generalization? Or is it instantiation syllogism, going from a big generalization to a particular? Well, it's actually inductive generalization, right? And although Trump will lose the election as a particular, what's really stated there is the majority of the people who actually vote will vote for Trump. So we're moving from a sample of 3,000 likely voters to all voters. That's a generalization. Okay, now try this one. 95% of Americans own a cell phone. Clint Yoder is an American. Clint Yoder owns a cell phone. So is this an inductive generalization or instantiation syllogism? This time it's instantiation syllogism. We are going down to the particular. And notice that we're back in the realm of induction because rather than saying all, we just say 95%. Okay. So here are the 4 sample arguments we've seen. The 2 generalizations are on the left, and the 2 instantiation syllogisms are on the right. I'm going to look in more detail at these 2 argument structures, but before I do that, I want to look at a particular kind of statement that is in all of these. So look at this. All swans are white appears in the conclusion of the first argument. All swans are white appears in the premises of the second argument. And then down here, rather than an all statement, we've got a statement with percentages. 57% of voters will vote for Biden in the election, right? There it's in the conclusion. And here we've got another statement with percentages. 95% of Americans own a cell phone. And again, now that statement is in the premises. So I want to take a second to focus on this kind of statement. And we're going to call it a quantified categorical statement. So this first section is on quantified categorical statements. And I'm going to jump over to video that I recorded earlier. Okay, so we're dealing with a certain kind of statement here that
Well, the first way to get used to it is just to think about examples. So here's some examples from the text. All Canadians are humans. Most physicists are smart. Few teachers are rock climbers. No dogs are cats. Some Americans are doctors. Some adults are not logicians. All of these are what we call quantified categorical statements. They are quantified categorical statements because, well, just look at the example here. Some adults are not logicians. It's got what we call a quantifier in it. It is a word or phrase that indicates how many. And then it's got two categories in it. And so in this case, the examples are adults and logicians. So the quantified categorical statement describes how many things in one category also belong to another category. So it's quantified, meaning it has a term saying how many. It's categorical because it contains two category terms. And then finally, it's a statement, meaning that it is a bit of language that can be true or false. It's not a question, it's not a command, it's a complete sentence. It makes an assertion about the relationship between two categories. So the first batch of exercises just asks you to identify the basic parts of a quantified categorical statement.
Yay, we're dissecting sentences.
Okay, yes, dissecting sentences. More, and then later arguments, and then we're back to critical thinking. So some of the examples are going to be really simple. In these cases, you're going to have everything's going to be explicit in the sentence and represented by an individual word or phrase. So some Americans are doctors. The quantifier is some. The first category we call the subject term, and that is Americans. Then there's what we call a copula, which is just a form of the verb to be, and almost all of the time it's going to be are. It might be the singular is, but mostly it's just going to be are. And this is just something that couples together the subject term and the predicate term, the two categories. So in this case, the second category is called the predicate term, and that is doctors, right? The only thing you have to worry about here are some tricky cases, because what we're doing is we're standardizing English, which has all sorts of irregularities in it, and creating a more rigorous form. And so if we were in the formal logic class, a whole lot of time would be spent standardizing different kinds of English sentences into standardized sentences that could then be used for formal logic. But here we're just going to do a little bit of standardization just to indicate the range of sentences that can be treated using the kinds of tools that we're talking about. So consider this sentence. 30% of Canadians speak French. So what's the quantifier here?
30%.
30%. That's easy enough. What's the subject term?
Canadians.
Canadians.
Yep.
But we don't have an are, we don't have a copula, and instead of a subject, instead of a predicate term, we've got this verb phrase, speak French. Now you have to remember that categories are always defined by noun phrases. So we want to change the verb phrase here into a noun phrase so that we can talk about the quantified relationship between two categories. So what we're going to do is we're going to say that the copula is implicit and the predicate term is just people who speak French. And so in general, what we're going to do in this kind of situation is we're going to take this verb phrase and we're going to add people who or things that in front of it to turn it into a noun phrase, right? So we've got some exercises here. The copula can be implicit, and sometimes the predicate must be transformed into a noun phrase. So why don't you, I think I just have 7 quick examples on the sheet I handed out. Take a second to do those, and then we'll start to talk about arguments that use quantified categorical statements. So when we talk about the terms, actually what's going to happen is we're going to wind up breaking those into variables and values, right? And actually, let me take a step back. So in the previous section, we identified what a quantified categorical statement was and looked at its parts. Now we want to bring in some more terminology so that we can start to apply more actually ideas from probability and statistics, right? So when we have a category, let's just take the sentence, 50% of the balls are blue, right? The predicate there, things that are blue, is actually a specific value that can be taken by a variable, which we could label like color, right? Often what happens is our first category identifies a whole population that we want to study, and our second category identifies the values that a certain variable takes, right? So the variable is just a property of individuals in a population that can take many forms, and the values are the different forms the property can take. And for a lot of the examples we're going to be using, because we're drawing a little bit on statistics here, what we want to do is take, we're going to be using the example of balls in an urn, because that's just tradition for statistics. So you can imagine that the balls might have a number of different properties. They might be different sizes, they might be different colors, but so here the variable is color, and the values that variable can take are red and green, right? So here's a sentence that I use in my ethics class when I'm talking about statistics, because we do actually statistics and ethics, funnily enough, because we study eviction. And so here's a statement. It's a quantified categorical statement. 1 in 8 Milwaukee renters experienced a forced move. This is about a study of eviction in Milwaukee a little bit ago. But in any case, so what's our quantifier?
1 in 8.
1 in 8. What is the subject term?
Milwaukee renters.
Yeah. And what's the copula and the predicate term?
The copula is implicit,
Yes.
and the predicate term are people who experienced a forced move.
Right. So 1 in 8 category, Milwaukee renters, are implicit copula. Category, people who experienced a forced move. Right? So we can say that Milwaukee renters is a variable f, and people who experienced a forced move is a part of a variable g, right? And then what we would say is the variable Milwaukee renters can take 2 values, and that's just going to be yes or no. And then people who experienced a forced move takes 2 values, yes or no, right? So I'm mixing together some ideas from different ways of studying quantified categorical statements, just to give you a variety of tools. But if we were, when we're analyzing some empirical science, this is generally the way I phrase things. Okay. So we want to, in this section, we're concerned with two styles of argument. Previously, I said that when we were doing critical thinking, we would identify various argumentation schemes, right? You had a basic idea, which was to put arguments in standard form with premises and conclusion marked. Argumentation schemes are subtypes of standard form where you have certain kinds of premises and certain kinds of conclusions. So we did argumentation schemes for arguments from authority and arguments by analogy. Now we're going to do two more argumentation schemes: inductive generalization and instantiation syllogism. And the difference between these is essentially where you have a quantified categorical statement.
Okay, but before we go on to talk about the argument schemes for inductive generalization and instantiation syllogism, I just want to run through a few of the homework problems on quantified categorical statements. So here's the sample problem. The sentence is, some dinosaurs had feathers, right? So here we go. The quantifier is straightforward. It's some, right? That's easy. The subject term is straightforward. It's dinosaurs. Again, though, we get to this thing where rather than having an copula and a noun phrase, we have a verb phrase, had feathers. So we change that to saying that the copula is implicit and the predicate terms is things that had feathers. Okay, now let's just hit a few from the problem set itself. Some politicians are not members of tennis clubs. Again, the start of this should be easy. The first two, I mean, for all these, it's like quantifier is the first term, because I'm not doing tricky problems here. And the subject term is the second word, right? Some politicians. So now you have to ask, is there a copula here? Yes, there is. Are is a copula. Now, the predicate says not members of tennis clubs. We need that to be a proper category phrase. So we can change that just to make it smoother to people who are not members of tennis clubs, something like that, right? All dogs go to heaven. Again, it starts easy. All and dogs. Now we've got go to heaven. Go to heaven is a verb phrase. There's no, it doesn't say is or are here. So we want to say that the copula is implicit. And the predicate term we need to rewrite. We can say things that go to heaven, or animals that go to heaven. I use things as sort of the most generic term possible. So, yeah. Okay. Next one actually is a little tricky up front. Most is the quantifier. At this point, a lot of people are tempted to just say things, but look at where the copula is. Copula is after fridge. So the subject term is all of things in the fridge. Are, and moldy is an adjective. We want to make it a noun. So things that are moldy. Some birds do not fly. This works just like all dogs go to heaven. So some birds, implicit, things that fly. Or we could say animals that fly. Either way.
That means that if you say something in class, just fair warning, the audio will appear online. And I post these videos to YouTube because it's the simplest way to do it. So if you don't want to have your voice online asking a question about generalizations, just tell me and I'll pause the video. But it's just fair. Okay, inductive generalization. This is our first style of argument. Again, we've got a population, which is a group of things with a property. And in an inductive generalization, this is going to be this is the larger group of things that you want to draw a conclusion about. The population is going to be in the conclusion. The other term we need is a sample. A sample is any subset of the population, right? And in an inductive generalization, the sample is the smaller group of individuals that appears in the premises, right? So generalizations move from samples to populations, right? So an inductive generalization, we can define it as an inductive argument with a quantified categorical statement in the conclusion and a quantified categorical statement about a sample of that population in the premises. So there are two quantified categorical statements often. One's in the premises and one's in the conclusion. The one that is about the bigger category, if that's in the conclusion, you're making a generalization because you're moving from a sample to a larger category. And if some of the language around this appears messy, I'm moving from a different way of analyzing it, which I picked up from a previous co-author, to this way of doing it, which is simpler. So, and more in line with things, with the way people talk when they don't have degrees in philosophy. But in general, the idea is still the same here. We're starting with particulars, we move to a generalization. So this becomes the argumentation scheme. In a sample of things with the property F, X% of them also have the property G. Conclusion, in the whole population of F's, roughly X% are G. Right? And then, so what we're doing is we're moving from a premise that's about a small group to a conclusion that's about a large group. So, whenever you encounter an argument, I'm just reiterating the basics, we want to ask, are the premises true? Do the premises support the conclusion? And is there any information that's missing? With, do I need to hit all of this? Yeah, let's get this. With inductive generalization, we want to focus on two questions that we need to use to decide whether the premises would support the conclusion. Is the sample large enough? And is the sample representative? This is where we get into the language of statistics. So, one thing that happens here that's important to realize is once you start applying levels of statistical rigor to generalizations, pretty much any generalization you draw in the course of ordinary experience is going to be weak, right? And so one thing we have to think about is, because we're always making generalizations based on ordinary experience, we couldn't walk through the world without it. We need to think about, again, actually lowering our standards of evidence from even statistical significance. With a lot of argumentation schemes, there's a fallacy that goes with the argumentation scheme. And the fallacy is the name of the bad form of the if I teach a full unit that's just about fallacies, I say every fallacy is the evil twin of a good argument, right? So with a generalization, the evil twin of an inductive generalization is a hasty generalization, right? So it's a fallacy that is committed when you make a generalization based on a sample that is small or biased. Okay. One of the things that you have to do in the exercises is assess inductive generalizations. So in order to do this, we need to know some of the language of for understanding populations and sampling. A margin of error. This is a phrase we hear a lot. If you listen to the news, anytime a poll comes up, they will mention margins of error. It's important to know what it is and it isn't. So the technical definition is it's a range around the frequency of a trait, that is the quantity of a variable, in a sample such that we can be 95% sure that the overall population is in that range. So when you move from a sample to a population, if you want to be 95% sure of your generalization, you need to add this margin of error, right? This is a purely mathematical property that is a relationship between the size of the sample and the size of the population. And it is assuming that the sample is random, right? So even when you see a poll that says, oh, clearly Biden is going to win, his lead is well outside the margin of error, there are still other ways it can go wrong, right? The margin of error does not take into account, for instance, sampling method. In the other reading I had you do from Southworth and Sawyer, which is the book that we're going to be using for a lot of the stuff on cognitive bias, they talk about the old-fashioned method of survey sampling, random number dialing, right? You just dial numbers at random, and once upon a time, within my memory, random number dialing was a reliable way to get a random sample because people picked up the phone for random numbers. There wasn't a distinction between cell phones and landlines. Everyone had a landline. You were picking up a landline, you'd pick it up no matter who rang, you'd probably answer a question. In the cell phone era, the random number dialing is just not as reliable anymore. None of that would be taken into account in calculating margin of error. Margin of error is just about the mathematical relationship between the sample and the overall population. So I just want to give you a few, this slide just mentions what I just talked about. But I want to give you a few rules of thumb that are useful for evaluating sampling when you see it like in a newspaper. Either the two I encounter most are political polling and health news about there's a new cure for bad breath or whatever. Given a certain set of assumptions, the margin of error always falls in a certain range. So if you have more than 50,000 individuals in your population, the sample size you need levels off. I don't have a graph of the curve here, but if you're trying to guess something about more than 50,000 individuals, you're not going to get much more benefit from larger samples. The other thing is that if sampling size is easier to guess, if you know that the samples is close to 50-50, like, you know. Given those two assumptions, we can say that a sample of 1,000 individuals gives us a plus or minus 3% margin of error, right? Am I doing this right? Yes, I am so. And this is what most statistical surveys, most political surveys will shoot for, right? So here's the population size. With a population of 50, to get a sample of plus or minus 3%, you basically need to sample everyone, right? But after a while, as the population gets bigger, the number of people you need to sample levels off, and it doesn't do you any more good. So for the larger populations, if you're trying to make an inference about, for instance, all of America, having a large sample becomes less important than having a representative sample. And the classic example that's brought up in Southworth and Sawyer is the 1934 presidential election. I hope I'm getting the date right. But it was FDR versus Alf Landon. And a very large survey concluded that FDR would lose in a landslide. But the survey was based on, I believe, car registrations. And in the 1930s, you had to be pretty wealthy to have a car. So even though it was a larger sample, it was a biased sample. A young pollster named George Gallup did a sample that was only like 1,000 or maybe 3,000 people, but it was genuinely random. And he correctly predicted the outcome of the election. And so this is often now used as a kind of parable for the importance of genuinely random sampling. All right. So, like I said, for large populations, getting enough people isn't as important. Well, you reach a space of diminishing returns for large samples, and what you really need is a genuinely representative sample. So these are some things to be on the lookout for when you're looking at sampling methods. A genuinely random sample is what you want. A genuinely random sample means that each member of the population has an equal chance of being in the sample. A lot of times, even, in science, rigorous published science, you don't get genuinely random samples. Often getting genuinely random samples for human beings would be unethical. You would, for instance, have to randomly give people disease, which has been done, and has been done by American doctors. Now I'm getting off into my bioethics course. In the Philippines, in the early 20th century, American doctors conducted highly unethical experiments on prisoners. That amounted to giving people diseases at random. But generally, you're not supposed to do that. And there are plenty of other examples of unethical experimentation in the history of American medicine. But generally, there are two other kinds of samples that you will encounter. A self-selected sample is a sample in which people choose to be in the sample. You put out an advertisement that says, here, come talk to me, engage in this experiment. Self-selected samples have very particular biases. They tend to overrepresent outliers. Anytime you have a web poll, you're dealing with a self-selected sample. people have to choose to click on your poll. People tend to choose to click on polls when they have, for instance, strong opinions, right? So if you're doing political polling, people with strong opinions in any direction will be overrepresented for a self-selected sample. Another place this comes up is with sex surveys. Almost every sex survey uses a self-selected sample because people don't like to talk to strangers about sex. So who is willing to talk to a total stranger about sex? Well, actually, it turns out people with unusual sexual practices. So actually, what's a good phrase here? I'll just say, people with sexual practices that aren't represented in mainstream media tend to be overrepresented in sex surveys. This goes all the way back to the 1950s with the Kinsey report. Okay. Sample of convenience. This is a sample of individuals that happen to be accessible to the researcher. This is the most common kind of sampling in psychology. Most psych tests, things have probably changed in the internet era, but for the longest time, most psychological testing was conducted on freshmen in intro to psych classes because they were accessible to the experimenter. Notice that freshmen in intro to psych classes are not representative of the overall population. Young people, 18 to 22, generally from wealthier backgrounds. Bunch of things like that. Another one that comes up is all the patients in a certain hospital, right? I'm just sampling the people that happen to come into the emergency room in LA or wherever. One final kind of sample I want you to be aware of is what's called a stratified sample. A stratified sample is a way, when you can't get a completely random sample, to try and approximate it. And so what happens is you divide the population into specific subgroups to ensure that those subgroups are represented properly. So in the Milwaukee area renters study, which gave the statistics about eviction for Milwaukee that I use, what the researchers did is they identified majority black and majority white neighborhoods, and then balanced the number of black and white neighborhoods to match the overall distribution of the overall population for the city, right? This way they're ensuring that that value is adequately represented. And then within those, once they identified neighborhoods, they picked blocks at random and surveyed everyone in that block. It's not a fully random sample, but it is as close as you can get in many circumstances. And a stratified sample, most of the time, is going to be a better sample than a self-selected sample or a sample of convenience, which have known biases. Right? All right, so the next set of homework problems asks you to look at inductive generalizations, put them in standard form, and I needed to update the phrasing on the question here because it mentions things like warrants. Don't worry about that. Just put it in standard form for a inductive generalization, and then ask the two crucial questions. Is the sample large enough? and is the sample representative? Just using the rough tools that I've given you so far. Pair up in groups and talk about your answers, and then we'll go over them together.
Okay, let's just take a look at a couple problems from the next section before we go on to talk about instantiation syllogism. So for these, you needed to put the argument in standard form for inductive generalization, and then discuss the size of the sample and the representativeness of the sample. And in the example here, I've got it done. I do all of the standard forms with two premises, which is a bit more complicated than the version of inductive generalization that I'm giving in the current PowerPoint. So I'm going to show you how to do it two ways. And it's kind of a trivial difference, and you would get credit for doing things either way. Let's just start here. On December 1st, 2005, a phone-in poll of 404 Fox News viewers found that 87% believed that schools, courthouses, and other government buildings should be allowed to display Christian Christmas imagery. We can conclude, therefore, that about 87% of all Fox News viewers believe this. So the way that I used to do this and the way that it's done on the answer sheet is with two premises, and it's the first premise would just look like this. In 404 cases, the property of being a Fox News viewer was present, and then in 87% of those cases, the property supporting public displays of Christmas imagery was present. And then, putting it this way, forces you to identify the two separate properties that are part of the quantified categorical statement, right? Your F property and your G property. And then the conclusion would be that 87% of Fox News viewers support the display of Christmas imagery now on government buildings. Now, one important thing to see here is that this conclusion is just about Fox News viewers, right? When you're analyzing whether the sample is biased, you might say, well, it's a sample of Fox News viewers, so that doesn't represent the country as a whole. It's a biased sample, which is true. But the conclusion is also about Fox News viewers. So simply the fact that they polled Fox News viewers is not enough to make it to make it biased, right? Because you've got the same group in the premises and the conclusion. Now, actually, the way I want to start people to start doing this is just with one premise, which will make things simpler. So what you could do is you could say, in a sample of 404 Fox News viewers, 87% supported hang on. 87% supported Christmas imagery on government buildings. And then the conclusion can be, therefore, in the whole population of Fox News viewers, 87% support. Right, whoops. And here, let's make this pretty. Um, and we'll move the line down too. I'm taking up your video time being finicky. There. That's a shorter version of it. And that emphasizes the idea that in a inductive generalization, you're moving from a sample to a population, right? All right, so now we want to assess the size of the sample and the representativeness of the sample. The size of the sample is 404 viewers, and that's pretty small. The thing you want to look at here is this PowerPoint slide. So when you're dealing with populations of over 50,000, and there are millions of Fox News viewers, you can use these rule of thumb. You can use this rule of thumb for margins of error. 500 people will give you plus or minus 5%. Most political polls shoot for plus or minus 3%. This is less than 500, so that's pretty mediocre, right? And the representativeness, like as I said before, the sample is of Fox News viewers, but the conclusion is also about Fox News viewers, so that's not a problem. The problem is that it's a phone-in poll. That means it's a self-selected sample. Self-selected samples overrepresent people who are, in politics, politically radical. In general, they represent outliers, overrepresent outliers. Okay, for the next one, we have a case of ordinary reasoning, and it highlights again the fact that everyday reasoning never rises to the level of statistical significance. So this is a person who has two dates with men. They are both dates are very handsy, and she concludes that men only want sex. So you could do it with two premises if you're following the example I gave. In two cases, the property being a man was present. That's your F. In 100% of those cases, the property of only wanting sex was present. That's your G. Conclusion, men only want sex. If you do this as a single premise, it's going to look like this. In a sample of two men, 100% only wanted sex, right? And then the rest would just follow from there. And again, this one's pretty straightforward. It's clear that this is not a representative sample. The sample size is minuscule, and the sample was selected. It's not quite a self-selected sample. It's selected by the person speaking and the person who chooses to date the person speaking, right? So the sample is the people she chose to date and who also chose to date her, and therefore is not representative. It's pretty straightforward. Okay, to wrap things up, let's look at inferences going the other direction. Rather than making generalizations, we want to start with generalizations and apply them to people. So we call this the instantiation syllogism. In general, it's reasoning from a generalization to a particular. More specifically, it's reasoning with a quantified categorical statement in the premises and a statement about an individual in the conclusion. So with our swan thing, we might start with a generalization that all swans are white, and then go down to the particular that Odette the swan is white. And again, actually, if you really have the word all there, we're suddenly being deductive. It's valid. But that just means that your generalization at the top is risky. And most of the time, your premise is going to be something like all the swans I've seen, or, 87% of, something like that, in which case it's, we'll be back with induction. Okay. So the argument scheme for this is really straightforward. X% of F's are G. This is an F, so this is a G, right? And the critical questions we want to ask here are, so the critical questions we want to ask here, the specific critical question for this argument form is a spin-off of the third kind of critical question that would apply to any argument. So whenever you have any argument, you can ask, are the premises true? Do the premises support the conclusion? And has any relevant information been omitted from the premises? When we are talking about the instantiation syllogism, it's the third general critical question that we want to have a specific form of. And that is the thing we're looking at a typical F for whatever property F we're looking at? So this amounts to saying, has there been some important property of this individual that's been left out? For instance, at the start of this, I gave the argument that 90% of Americans own cell phones. Clint Yoder is an American, therefore Clint Yoder owns a cell phone. Well, suppose there's some hidden information there that Clint Yoder is Amish. Suddenly, that argument no longer works very well because the individual is no longer a typical example of the generalization. So that means that with this argument scheme, there are kind of two fallacies, or there's a principle and then a fallacy. The principle of total evidence is just a rule that says you should take into account everything you know about a particular when making an inference about it, right? So if you know something that changes the generalization, you have to bring that in. And if you fail to bring that in, you're committing the fallacy of suppressed evidence. So for instance, 1 in 6 people on Earth is Chinese. There are 6 people in my family, therefore one of them is Chinese. That doesn't work. Actually, the odds depend. For my family, it's gonna, the suppressed information is that we're white. For another family, the suppressed information might be that they're all Chinese. But either way, you're leaving out information, right? That means that going from the generalization to the particular is fallacious. All right, let's just look at a few of problems from the last homework set. And in this section, you have to decide whether what you're looking at is an inductive generalization, are you moving up to a generalization, or an instantiation syllogism where you are moving down to a particular. And we're going to look at some examples of each. So the vast majority of people with advanced cases of lung cancer will die from the disease at some point within the next 5 years. Our good friend Henry has an advanced case of lung cancer. Unfortunately, then our good friend Henry will die in 5 years. Actually, I need to put the word advanced in here. Advanced. So when we do this, the first thing to see here is that this is instantiation syllogism. So we're starting with a generalization. The vast majority of advanced lung cancer patients die in 5 years. And then we're moving to a particular. The conclusion is about a single individual, Henry. The quantified categorical statement, the generalization, is in the premises. So this is instantiation syllogism. It uses this 2-premise format, right? And the question we need to ask here, because this is an instantiation syllogism, is this a typical case? And there might be reasons why it's not, and that information just isn't given. I mean, maybe Henry had very successful surgery, very successful lung transplant, something like that, right? So we need to know more about whether this is true. Okay, number 2, lottery winners are disproportionately male, about 65%. Oops, that punctuation is screwed up. We want that. There we go. Last week's lottery had a winner, therefore the winner of last week's lottery jackpot was male. So 65% of lottery winners are male. This is a case of a lottery winner. Here's a lottery winner. In this case, the winner is male. Again, this is instantiation syllogism. You're moving from a generalization to a particular. This particular lottery winner, you've got the statistical statement, the quantified categorical statement, the generalization in the premises. To my mind, 65% is too low to make the argument cogent or even strong, but your mileage may vary. All right, I'm going to scroll down and look at one that goes the other direction. 11% of the customers at the Weeping Creek Mall who tried a sample of the new Lando Lard bite-sized bacon strips went on to buy at least one packet of the product. And then we draw a generalization about all samplers. So actually, let me rewrite this in the form. So right now it's got 2 premises. Let's write this with 1 premise to make it absolutely clear that this is a generalization. So P1 in a sample of customers at the Weeping Creek Mall, 11% in a sample of customers who tried a sample of a product, bacon strips, 11% went on to buy the product. And then we can say for the conclusion, in the whole population, 11% of people who sample the product will buy it. So you can see that this is an inductive generalization because you're moving from a sample to a population, right? And furthermore, well, that's enough right there. The other thing that's interesting is that a lot of information is missing from this. We don't know the size of the sample. We also don't know how much what the population we're inferring to is. Is this the population of America, people on Earth, people at the mall? It's all vague. So we don't know enough about the sample size. We also notice that the sampling method is probably convenience. So that means that it's probably also not reliable. The argument as a whole then is weak. All right, so the answers to the rest of these will be online. And then for class 12, we're going to have a review day.